So what I thought I'd do with the time that we had here today was to, instead of auguring into all the technical details about the Parrot Tailings waste removal project, I would start in the bigger context and describe sort of the state's thought process about how we came to decide to remove the Parrot Tailings. Now, with that said, I do have to mention a disclaimer. What I have to say here today are my own personal thoughts and perspectives. I'm not here representing the governor as the trustee for the state of Montana, and I'm not the state of Montana. I'm the project manager for this project. But I wanted to lay out what we've gone through over the last 5 or 6 years in developing what turned out to be the Parrot Tailings waste removal, and then I'll talk about the Parrot itself. So this I think will help give context to how we ended up where we're at, because there seems to be a lot of confusion when I get questions about why we're removing the Parrot Tailings, why, say, BP ARCO isn't doing it or EPA's not doing it. So, for those that you don't understand what natural resource damage and natural resource damage claims are, I'll just have a couple slides to explain that, because it's a little different than remedy under Superfund laws. So what laws allow us to recover money for restoration? So there's the main component under Superfund law requires remedy, which is what EPA and DEQ do under that you see around the valley for cleanup is remedy, but it also requires restoration activity. And at Butte, restoration, the only restoration trustee is the state of Montana. And if you want to think about it, what restoration is, say for example, you have a contaminated aquifer here. Now remedy can make sure that contaminated groundwater is safe for people not accessing it, and that would be the remedy for groundwater. Restoration is making sure that the public is made whole because we can't access that groundwater anymore. So we, through settlements or through litigation, can take responsible parties and make sure that we are, as public trustees, are made whole for that damage to those natural resources. And these are allowed under, it's both allowed under Superfund law, and if it was an oil spill, it's allowed under a law called OPA. So remedy and restoration are required under statute to work together. Now, it doesn't always seem that way, especially here in Montana and especially on these Butte sites, but it's a requirement that we work together with the regulatory agencies. So the goals of the remedial action, again, this is what EPA is in charge of, is to eliminate, reduce, and control risks to human health and the environment. It's not to get things back to where they were before the release. That's what we recover for, or what we try to achieve. Natural resource damage regulations establish an amount of money to be sought as compensation for those injuries to natural resources resulting from the release. So the definition of restoration is any action or combination of actions to restore, rehabilitate, replace, acquire the equivalent of the injured natural resources. So in my example of groundwater in Butte, we have injured resources in Butte of groundwater. We recovered a large sum of money for groundwater in Butte, and we used that money to do things like build the Basin Creek water treatment plant, to upgrade the water system within Butte, the water pipes, to improve the water pipeline coming over from Silver Lake. We've done all sorts of activities to replace that. Those are primarily replacement activities for that resource. So Montana's NRD program, we are established in 1990. The governor, as I said, is the trustee. We represent the state, and that includes Fish, Wildlife, and Parks, DEQ, DNRC. The governor has an NRD policy committee, which includes his chief of staff, the directors of these various departments and the Attorney General. We're attached to the Department of Justice, and we're organized. We have a litigation component, and that's where we recover damages, and a restoration component, and that's where we implement these restoration activities. And we have about 12 FTEs. All those folks, except for Pat, as you all know, are located in Helena. So let's talk about Butte specifically and what is called Butte Priority Soils Operable Unit. Again, that's EPA's label for where the Parrot is. What are the remaining surface water quality problems in BPSOU as the state sees it? So this is getting to why we're doing the Parrot. So what we did starting about 6 years ago was look at what are the remaining issues that we thought that needed to be tackled within Butte. We looked at the mine wastes that are still along the creeks. So there's mine wastes along Blacktail Creek, there's mine wastes along Silverbow Creek. And these wastes are both a surface water problem and a groundwater problem. This groundwater problem discharges into surface water, right? So we have the three main areas are the Butte Reduction Works, the Confluence area, and what is called Blacktail Creek. So that's west of I think it's called Livingston Avenue? Lexington Avenue, thank you, Josh. These are all Tier 1 sites. The other Tier 1 area is obviously the contaminated stormwater that comes off the hill. So these were the #1 priority areas. And I'll show you a figure here so you can see where these are geographically. Tier 2 areas were mine wastes that are contaminating groundwater that then discharged to the creeks. That included the Parrot, Diggings East, and Northside Tailings. And then the Tier 3 area were various mine wastes on the hill that impacted stormwater. Now we've already identified stormwater as a Tier 1 area, but if you address these Tier 3 areas, you'll reduce the stormwater. So here's a figure that shows these wastes that are along the creeks. So to orient you, here's Montana Avenue, here's the highway, here's Blacktail Creek, here's Upper Silverbow Creek, here's the Confluence area. So there's waste in the Confluence area, there's waste here in Blacktail Creek, and then we have this large area called the Butte Reduction Works, which, similar to the Parrot, was an old copper smelter originally. It was also a manganese enrichment facility, amongst other uses, but it started out as a smelter. So these areas not only allow direct erosion of waste into the creek, but they have groundwater saturated waste, and that groundwater discharges to the creeks. So that's a problem that we noticed that was a Tier 1 problem. Then we have these basins and these stormwater areas, that are a problem. So we have stormwater coming off the hill, it's contaminated, and it discharges to the creeks, which is also a problem. And then the Tier 2 areas, we have wastes, the Parrot, Northside Tailings, and Diggings East. And I'm sorry, these colors don't show really well. This is, to orient you, this is Upper Silverbow Creek, formerly known as Metro Storm Drain. Here's Blacktail Creek. We have the Diggings East waste, Northside Tailings waste, and here's the Parrot. All these areas contaminate groundwater, and that groundwater in part discharges to the creeks. Now, I know there's another component here. There's a subdrain that in part captures groundwater, and I'll talk about that in a minute. But these are Tier 2. So what we did was went through and we had to guess, like, what components of these remaining activities were EPA going to require BP, ARCO to address, and what weren't they? And what stuck out was that we thought, more than thought, that we were told that the waste along the creek and the stormwater ARCO BP were going to be required to address, but they were not going to be required to address the Parrot. And the Parrot, from our investigations, so we had numerous investigations, and I'll talk about that some, we saw as the largest loader to the groundwater system. Now, I'm not saying that the Parrot was directly discharging to the creek as of yet, but it was certainly the largest loader to the groundwater system. So, as most of you know, there's a subdrain in place below Upper Silverboat Creek. And that subdrain was originally constructed to keep the heavily contaminated groundwater from discharging into Upper Silverboat Creek and becoming a surface water problem. Historically, that was a serious surface water problem. Now, with the construction of this subdrain, it certainly is very effective in addressing that problem. We don't have that problem anymore. The problem that has now occurred is that it's been sort of reinterpreted that this subdrain captures all contaminated groundwater. And the state has never thought and does not think that that's true. Again, this subdrain, I don't have a good figure of it here. It sort of has a vault down here and is underneath this Upper Silverboat Creek, starts around, there's a cell tower right around here, and is underneath the capture. So if you think about the geometry of the situation, we got flow down the hill, and you got a capture system that's horizontal, but in parallel to flow, so the geometry of it's wrong, and it's not vertically penetrating. So we've got three-dimensional flow here. So we've got a couple geometry problems with it. Now, it is effective as it is effective at what it was originally intended to do, which was keep groundwater from discharging into this channel. But was it ever intended to capture all this? No, otherwise it would have been oriented 90 degrees to what it was constructed as. So we know from data collected in the creek and various studies that there's still contaminated groundwater discharging to the creeks. And that's why we thought these large sources should be removed. So this is what that pipe looks like. See this slot here? That's the opening to the pipe. There's two of those. And these slots, because of the design of this, where this pipe is laid, it's oxygenated. These slots are clogging. The gravel pack around it is clogging, and these slots are clogging. And eventually, if this is a permanent feature that's going to have to last forever, this pipe is going to have to be replaced. This is how it was installed. You can see the gravel pack. This is the bottom of the Upper Silverboat Creek. There's a liner system in there, although I think it's been breached a number of times. It doesn't seem to be all that effective because our wells outside of it seem to rise and fall with water in the Upper Silverboat Creek. Here's sort of a picture. It doesn't really show up all that well with this light, but this is the real problem. You can see the precipitates here in the gravel pack, all this red iron staining. So this pipe is cleaned regularly, but it'll come to a point where cleaning the inside of the pipe isn't going to affect the outside. And you can see the tailings and the iron staining out here on the side. So this is the tier 3, the wastes on the hill that are going to be addressed, that ARCO's agreeing to address on the hill. So that's the basis for why the state decided to remove the Parrot, because it was the one area that ARCO was not going to be required to address. So how do we know all this? How do we know that their wastes along the creek were a problem, that groundwater is discharging to the creek, that diggings east is a problem, or north side, or the Parrot, or any of this? And I'm not going to go through all this, but it's because we spent years and millions of dollars studying it. The state of Montana did with money that we recovered. We investigated it. BP refused to investigate it. EPA would not require them. So We, through much hard and diligent work of the Bureau of Mines, contractors and consultants of ours, investigated the Parrot, the Diggings East area, Blacktail Creek in the confluence area, and even in the last couple of years, the Butte reduction works. So we investigated these sites as well as the creeks themselves to make these determinations. So what's wrong with the creeks? Surface water in the creek continues to exceed state standards for copper, zinc, and other contaminants during low flow and high flow conditions throughout the operable unit. We have also shown that in-stream sediments in the Butte reduction works in the confluence areas, as well as Blacktail Creek, are recontaminating the remediated Silverbow Creek. So the state of Montana settled with BP ARCO for almost $100 million to clean up Silverbow Creek, and the state cleaned up Silverbow Creek. And now we're finding out that these contaminated sediments are flowing down into Silverbow Creek and recontaminating that, and the state wants it to stop. We don't want our investment impinged upon. The thing that you need to understand is in-stream sediments, there's two pathways for contaminated in-stream sediments. They can come down from above, from sources. They can also be impacted from contaminated groundwater discharge into the creeks. So groundwater, as some of you know, groundwater is quite a bit different geochemically than surface water. And these sorts of contaminants come out of solution when they discharge to surface water, and they contaminate these sediments. So in-stream sediments are sort of the canary in the coal mine for, if you want to say, for groundwater discharge. So I'm not going through all the data that we collected because it's, I mean, there's dozens of reports, but here's just one recent report, just one data set for one area. This is Blacktail Creek, and this is various data. This is groundwater data, soil data, in-stream sediment pore water. So we look at the pore water in between the sediments to look at what bugs are exposed to, which is what fish try to eat, right? We look at the in-stream sediments themselves and test pits. So this is just one effort in one location. This is sediment data, again, from one effort, looking at in-stream sediments. Again, here's the Butte reduction works, Blacktail Creek, the confluence area. Here's upper Silverbow Creek. But we went way upstream to look if there were sources. And the red numbers, just to give you some sort of indication, the red numbers are things that are in exceedances of what we call these screening benchmarks. There are no standards for in-stream sediments, but we have some EPA-determined screening benchmarks. So you can see pretty much everything's red. And then many times, they're 3 or 4 orders of magnitude above. So in 2014, we came out with a conceptual restoration overview of some of these areas, what we thought would be good ideas for how they should be cleaned up. And we had a number of public meetings to go through them with the public. Now again, the state of Montana is not responsible for cleaning these areas up. That's BP ARCO's responsibility. But here's an example. This is Blacktail Creek. This is after all the waste is removed. Trying to reroute the creek. This one option had a pond in here. FWP really didn't like that because they were afraid people would place fish in here. BP also didn't really like this one either because this included removing all the waste. But we had cross sections. We looked at how much would have to be removed, how much you'd have to backfill. Here's one of Diggings East, if you know that area, North Side Tailings. So this is upper Silverbow Creek. We had upper Silverbow Creek put in a more looking more of a natural state. It's still conveying contaminated stormwater. Again, we had some ponds and some walking trails, regrading it again after all this waste was removed. So we were tasked by the governor's office in trying to push things forward so Butte could have some progress made. We know that it's been, BPSOU has been an operable unit for 40 years, and we were trying to get some progress made. So, why we moved on why the state moved on removing the Parrot was contaminated groundwater is discharging to both Blacktail and Silverbow creeks. And that contaminated groundwater is contaminated in-stream sediments and surface water above state standards or risk-based levels. So that's number one. Number two, the Parrot is the largest point source contaminant loader to the groundwater system. Here's a big one that isn't well understood. The Parrot is the largest contaminant threat to the creeks that EPA was not willing to make BP ARCO address. Waste at the Butte Reduction Works and Blacktail Creek, which has Silverbow Creek running right through them, and contaminated stormwater are more critical loading sources to the creeks, but apparently EPA is requiring BP ARCO to address those sources and pathways. So again, the Parrot isn't the number one priority. These are the number one priorities, but ARCO BP is addressing those. The Parrot's the number one priority that wasn't going to be addressed. So I know I didn't go through this before, but just to show it up here to give you some comparison in a numeric sense about what the Parrot groundwater looks like compared to, say, Berkeley pit groundwater, drinking water standards, or more importantly, in this case, surface water standards. Again, we're removing the Parrot to protect the creeks here. But if you look at, say, copper, for example, we're at a million parts per billion, and the surface water standards, 285. Zinc's at almost 500,000, and it's 2,500 is the standard for surface water. So again, if you look at Parrot groundwater, even though, granted, the Parrot is a mile away from the surface water, it's still you're still orders of magnitude above the standards. So the goals of our project are to protect the creeks, aquatic resources, surface water, and in-stream sediments from contaminated groundwater discharge, eliminate the known sources of the contamination, and enhance the creek's riparian corridors. So pretty basic goals of the project. Now, how do we do that? There's two basic ways in our mine waste activities that we do that. If you have all your waste is unsaturated by groundwater, infiltration's the only pathway, right? If we have waste sitting in groundwater, that's a pathway. So for number one, an appropriately designed cap can eliminate that pathway, infiltration. For number two, though, the only way you can address that is by removal. And for the Parrot site, we have both conditions. We have waste that only has infiltration as a pathway, and we have waste that are just sitting in groundwater and needs to be removed. So here's a photograph before the Berkeley pit was opened up and there was a wet discharge. This is Upper Silverbow Creek. Here's the Parrot off to the left. I think you guys can recognize the view. Here's the smelter itself. I'll go through a little bit of the history. 1890, here's a Butte map. Here's the Parrot up here. Here's Silverbow Creek. You can see they're utilizing the water already and damming it up. Here's the weed map from 1903. You can see again they're damming it up. In our excavation for this phase, we actually think we ran into that dam. You can see some of their slag piles out here forming already. This is a pretty famous photograph. Here's Silverbow Creek in the foreground. Here's somebody associated with the lawsuits that occurred in the Upper Deer Lodge Valley for the tailings being disposed on ranchers' property down there that occurred at the turn of the century. Here's a I think late 40s or right before the pit was open. The pit would be right up in here. Here's the Civic Center and the Parrot Tailings, but all these white areas are tailings except for this, I think, is a drive-in movie theater. But here's Diggings East, north side, and here's the Parrot in here. So you can see a lot of tailings, a lot of wastes. So what do we remove here at the Parrot? We're removing all groundwater saturated and groundwater unsaturated mine waste using the streamside tailings waste identification criteria. And that includes all this black clay horizon, and I'll talk about that in a minute. We're also removing all the slag. Now the slag has a much lower solubility, but it still leaches above surface water standards and drinking water standards. So, but this slag we're not taking off site. We're going to place under an area of the site to be protected from infiltration. So this is all laid out. We have what we call a Quality Assurance Project Plan, a QAP. We use the same waste definition criteria that was used on Silverbow Creek streamside tailings. Now, Silverbow Creek, right, has a creek running through it. We're a mile from the creek. Silverbow Creek's also, 25 years old at this point, but we thought this was a reasonable criteria to use. It was established and well understood and accepted. So this was the criteria we used for defining waste or not defining waste. Of course, nowadays we have XRFs, so we used an XRF. This was our adjustment criteria, but these are the numbers that we use to define or not define waste. So here are the materials types we had on site. We had our Butte Court monzonite. It was mostly overburden from the Berkeley pit, which was typically clean. Of course, we tested all these materials. We had a lot of poured slag. Again, we considered that contaminated. It was leachable. We removed and relocated that on site. We had the tailings themselves, leachable, of course. We had this organic black clay, old Silverbow Creek soil horizon. Again, very contaminated, much more so than the tailings. And then we had below this, we had this, what we called alluvium. And that may or may not have met our contaminated criteria depending on the sampling. So this is just a flow chart of how we handle these materials, and I'm not going to go through all that, but if you spend a little time with it, you'd understand how we would determine where materials were and how it was handled and how it was disposed of. But it's pretty simple once you spend a little time understanding it. So here's the outline of our excavation area. Now this isn't our whole project area, this is the excavation area. We have waste on this side that we weren't going to remove because it's not saturated by groundwater. It's all in the vadose zone and unsaturated by groundwater. And so we're building what is called an evapotranspiration cover system up here. So it's about 42 to 48 inch cover system that excludes infiltration from penetrating it. And so the pathway to groundwater is infiltration through those wastes. So it would protect those wastes in place. And the reason why we're leaving those wastes there, it's just uneconomic to try to remove all this infrastructure and remove those wastes. I mean, we would probably be increasing the cost of the project by 4 or 5 times, and we don't have that kind of money. And this makes it just as safe. The advantages of these ET cover systems are that they are, well, one, that they're very effective. They have low O&M because of their designs, their low engineered designs. They do have some high initial costs, but they have the low O&M costs. So they're typically not preferred by PRPs, but they're preferred by the public sector because of them. They allow light recreation. You can hike, you can have dog walking parks, falling on them. You can't have destructive sort of recreation. You can't have dirt bike parks on them or things that would erode the cap. They rely on vegetation to evaporate and transpire the moisture that they store in them. So what I'm going to talk about today is the phase 1, which is what we completed this year. And we've got the phase 2 excavation, and part of phase 2 is this ET cover. We'll construct that. I just wanted to throw this in here. This is our end land use. Now, this property is all owned by Butte Silverbow. This is their property. It's not our property. We have a written agreement with them on how we leave these end land conditions. We're not the developer of the land. That's Butte Silverbow and whatever agreement they have. We agreed on end land conditions. So we're replacing asphalt where we destroy it in these areas. We're going to compact and leave this area graveled for some expanded parking lot if they want to asphalt that in the future. And then they have these as what they're calling new commercial parcels, and then some green space over here, permanent green space. Again, that's Butte Silverbow. If that changes, our agreement allows us to change it, but we're not, those choices aren't made by us at NRD. We're allowed under statute to replace what's there. If somebody came in and say, hey, we want a water park here, that's not restoration, that's not what we do. Butte Silverbow could certainly do that, but we're not developer of the property. And so any sort of public process for how these, if it was decided they wanted to have a big park here, you'd take that up with Butte Silverbow. So here's an oblique view of the whole excavation outline. So orient yourself. Here's the Civic Center. Here's Harrison, thank you. Harrison, down here's the creeks, or Blacktail Creek here. Here's Upper Silverbow Creek. So groundwater's flowing down this way. Now, this is something else that comes out weird because you sort of see it in a lot of BP ARCO's figures. Groundwater flow is not just horizontal. It's a three-dimensional flow, right? And what we have here at the Parrot is some serious downward gradients. So there's a vertical component to flow. So flow is down here, it's up at the creeks. The creeks are groundwater gaining. And so when you look at flow maps without that component of vertical flow, it sort of distorts where water is coming and going. This is the first phase that we completed this year. It's phase 1. This was our initial modeling efforts of what the bottom of the excavation would look like. Okay, so these just figures never look as good as they do on the computer screen. So cleaner overburden, Berkeley Pit. Here's the Parrot Tailings. Now again, these tailings were reworked a number of times over the years. We've got this black organic silt clay. Now, that number is right, so 42 million parts per billion, right? So I'm not going to make you do the math, and I don't want to convert it because I use other parts per billion, but I'm not trying to mess you up. So that's 4.2% copper. That's what's in that black clay. Below that, we got this, it doesn't show up well here, but it's a gray medium sand, this alluvium. Here we got this Parrot groundwater, and again, it doesn't show up in this figure, but it's a blue-green tint. Now, we saw that in a well pair that was over here, and personally, I thought it was just sort of something was buried there. It was something unique. But what we found in this excavation is pretty much everywhere that we opened up that hole to groundwater, we found the same blue-green, million parts per billion copper, very high zinc groundwater. Now, we didn't always find this 4% copper, but we found 2.5% copper, percent copper, extremely high copper. So it's critical. It was critical to remove this. Now, this black clay right here, it's above groundwater. In other places, and over here below these shops, it's all below groundwater. So removing this stuff and then leaving this clay sitting in groundwater wouldn't make a lot of sense. Okay, so this figure shows where our ET cover is. Now you ask, okay, where's this stuff going? Here's our haul road. We made a deal with MR, Montana Resources, to bring the waste material up onto their property to what we call the stockpile location. And then they were going to take that material off and dispose of it on their operating facility. So it was quite generous on their part. What the two things that allowed was, number one, we didn't have to put any haul trucks out on public roads, right? So we would have had thousands of trucks out there. There's a risk and a danger with that we really want to try to avoid. And number two, it allowed us to use much bigger equipment, which made our project much more cost effective. So it was really a gift from MR to work with us on this project. This is just a couple pictures. Tailings, this poured slag, which was really difficult to get through and hard on the equipment. You can't really see on the bottom, but this black clay gets sort of smeared. Okay, this came out a little bit better. Poured slag, tailings. Here's your nice blue-green water. That shows up a little better, but that was everywhere that we got into. Tailings, the black clay. Here's a nice face of that alluvium where we did have exceedances of our waste criteria. But to give you some sort of idea, if this was, say, the black clay was, say, 1% copper, like 1 million, this alluvium might have been like 1,200, 1,400. It's above our waste criteria, but not at 1 million. But still, we have blue-green water. Blue-green water. Here's the first place we opened up the pit, and this is sort of the corner out near Civic Center Drive. You can see the elevated railroad track. So all the poured slag, what we did, we built out, we kicked out the bench on this elevated railroad track, evened out that slope more, and we're going to construct the ET cover over that area so it'll all be protected underneath it. So we consolidated that into one area and then put some in the sliver between the railroad track and Shields Avenue. Again, the blue-green water and the nice sort of cake-layered wastes. So one of the biggest difficulties on the site that we or the contractor ran into was this poured slag. And it was everywhere. It was more extensive maybe than we thought in this phase one. I think the good thing to say about it, the data that we have for the second phase doesn't look like we have any of the poured slag in the second phase, but we're going to confirm that here this spring. Slag, tailings, black clay. All right, so this is what we removed in that first phase. For simplicity's sake, I sort of lumped some things. Our clean overburden is just what that is. Slag is slag. And then this contaminated mine waste, I sort of collapsed the tailings, the slag, tailings, the clay, and any of that alluvium that failed all into mine waste. So you can see we ended up with a little less clean overburden, a little less slag, which was sort of good because it was so difficult, but we ended up with a lot more mine waste. Overall, our numbers weren't all that bad, almost 400,000 cubic yards. So it's only about 6% more, but our contaminated volumes increased by quite a bit more. The good thing is we still ended up finishing early, and we finished below budget, which our budget for this phase was $2.6 million, and we finished at about 2.4. So at about $6.27 a cubic yard, and that's primarily because we could use big equipment and didn't have to haul materials at any distance to a repository. So in large part thanks to having MR work with us. This is equipment that we used on the site, which of course is not appropriate for residential roads. So the things we learned is, trying to fully acknowledge obvious project complexities. Poured slag for us on this first phase was one. Groundwater saturated waste and waste segregation. Clear, concise definitions of materials to be moved and how you're going to identify them. Make sure that you have adequate identification and data for these wastes. So we're going to, for phase 2, we're going to collect some more data this summer to make sure we really have things locked down. Potholing all utilities, and you need to keep a close eye on your contractor. So one last thing I want to touch on is, so you do all this work, how do you know you made a difference, right? You just say, well, we moved all this waste and we, great. We didn't want to perform a project like that. We know this project has a high price tag, and so we developed what we call the performance monitoring, well, work plan, but it's a plan and that we've been implementing for over a year now. And the primary author of the plan was Nick Tucci. But the groundwater monitoring network, sampling methodology, and evaluation criteria to characterize the existing baseline conditions. So we wanted to know what were the current conditions for groundwater before we started the project, which also obviously includes the effectiveness of the groundwater collection system. And then we could see changes in time after implementing the project, how it's changed the groundwater system in a positive sense and any negative senses, right? So we wanted to establish this baseline condition, which we have. We've gotten a year's worth of baseline condition, and then we can look at changes over time. So we looked at existing monitoring points, we evaluated data gaps, we developed a monitoring network, which included, we installed approximately 30 additional monitoring wells in critical locations that we've been pretty much arguing with BP ARCO for the last decade about, which were primarily wells right adjacent to the subdrain. And then out of that data, we can formulate a conceptual site model for the system. So here's just a figure. I'm not going to go through it all. Nick's got a really good presentation on, but here's a figure of all the monitoring wells that have been installed over the last 40-something years. Now, don't let this snow you. I mean, some of these wells literally are like pieces of PVC sticking out of the ground with, drink cups on top of them. I wouldn't put the weight of anything on them, but we went through and tried to find everything that we could about all these wells to get the best network that we could. And this is what we came up with. It's looking at flow coming down the hill through these transects, looking at it at depths, and looking at changes. So we're looking at sort of a window through these areas. So here's the excavation. We have a well network up gradient of the excavation. Now it's not up gradient of the project because we got this ET cover here, but up gradient of the project, unfortunately, is on MR's property, and MR and BP have some issues around this area that we couldn't really get involved with. So this is the best we could do. Then we've got a transect right below our excavation. So this is sort of our sentinel transect that is, if we saw real geochemical changes, we'd see it here first. Now to give you some ideas, these green dots are new wells. Red dots are existing wells, but all these red and green dots are the wells that we're monitoring on a quarterly basis. So we monitor them for geochemistry, for water levels, and a few of these wells we even have in situ probes where we're taking consistent geochemical parameters, which wasn't being done before. And then down here we have a string of wells where we're looking at sort of sentinels, what's going actually into Blacktail Creek. So that's our network. Now, BP ARCO came up with their network. No, you can't see this at all, so I'm not going to talk about it. This is our analysis, what we're doing for our water quality chemistry. Conceptual site model. This is Argo's network. Now, I just want to point out, here's our excavation area. Here's their first. They're looking at like the effects of our excavation, and here's their first transect. And then you want your transects perpendicular to groundwater flow. Okay, that might work. Maybe like that. I'm not sure about this, and then you got a transect like this. I mean, this is implying, this is where we start having problems. This is implying, here's flow parallel to the creek, that there's not flow to the creek. This is just saying groundwater doesn't flow to the creek. So this is where we have like serious fundamental differences with ARCO. Now, we're going to sit down with them and we're going to try to work these things out. The other problem I have with this is, see these flow lines and stuff? They already have their interpretation on their work plan. They already know what's going on here before they've even collected the data. Usually you collect your data and then you decide what your data tells you is going on. You don't superimpose that. So what we're hoping to do is combine our activities and their activities and come up with one set of monitoring that we can all use, because as we all know, BP ARCO has a lot of construction activities in this area, and that's going to affect the groundwater system largely, and we want to know what all those effects are. So hopefully we can settle on something that we can all agree fairly represents the system. So I think that's it.